Good morning. Welcome to Krishna's classroom. We now enter the third phase of our lectures on Lebesgue integration theory. So far, what we have done is, in the first stage, we looked at the need to go beyond Riemann integral by looking at the shortcomings of Riemann integration. In the second stage, and after that, we introduced the concept of measure. That is a long process. Okay, how we get the measure to as large collection of sets as possible. And we also proved that there are some subsets of R which are not measurable. Then after the concept of measurable sets was introduced, we went to the second stage of considering what are called the measurable functions, which seems to be the ideal thing that we should do to get to the next stage. Now, having done that, now we are in a position to introduce the concept of Lebesgue integration and write down the Lebesgue integral of a integrable function. Okay. But before I start exploring Lebesgue integration, let me just make a couple of remarks on what I did until last time, especially the last two sections where we considered the Egorof's theorem and the Lusin's theorem. Okay, so some remarks on. So this is not a part of what I am doing right now. So remarks on and Lusin's theorem. Okay. So the first remark is that this is on Egorof's theorem. Egorof's theorem is true if the convergence is pointwise almost everywhere. So we bring this, we assume that assumed convergence is pointwise for the function. But now what we say that you can relax it and allow the convergence to fail on a set of measure 0. Still, the conclusions of the theorem will hold. And the limit function is finite almost everywhere. This part means that we are allowing So we said in the beginning that we are going to allow what are called extended real valued functions. That means it could possibly take value infinity at some points. I mean, that is possible. So such functions were also under our consideration. And what we say here is that the limit function, it is sufficient, and in the theorem we assume that the limit function is finite everywhere, and that part can be replaced by the limit function is finite almost everywhere. It says that still on a set of measure 0, the limit function may take value plus infinity or minus. Okay. The second remark is on Lucian's theorem. Lucian's theorem is valid if f is not necessarily real valued, which means again the same comment holds. That means it could take extended real valued, an extended real valued function, except that except for a set of measure 0, it should be finite. But may be finite almost everywhere. Now this is the general statement of the theorem. It says that in all these circumstances dealing with measure theory, lot of relaxation can be brought on the assumptions on a set of measure 0. So the assumptions of the theorem possibly need not be valid on a set of measure 0. Still the theorem would hold, and even the conclusion that you may have to modify, and the limit function, as in the case of Gross theorem, the limit function is finite almost every in that sort of statement. Okay, so that's about it. So the usual mode of proving these things would be that you mark out the set on which the assumptions would fail, and then take the complement of that, and on the complement, the what we have proved of Gross theorem or Lucian's theorem will be valid, and on that the conclusions of the theorem would hold. And what happens is that just where it could possibly fail, where the theorem may not hold, is only on a set of measure 0. That's all. Okay. So with these remarks, I mean, this I had forgotten to tell towards the end of the lecture. I should have done it last time, but it's okay, fine. Yeah. Now we come back to our theme of this part 3, namely introducing the concept of Lebesgue integral and then looking at the consequences. So let us briefly go through the scheme that we are going to take up. So Lebesgue integration. So we start with Lebesgue integration. We introduce this we introduce Lebesgue integral by first defining it for simple functions. So our strategy will be define first operation will be define Lebesgue integral for simple functions. Now the second stage is use the first definition to extend the definition for bounded measurable functions of a set of measures. Now extend the concept to bounded measurable functions over a set of finite measures. Over a set of finite measures. So that is the second step. There are two things here. Now you know that we have defined it for simple functions, and simple functions are bounded measurable functions over a set of finite measures. So you go beyond that. How do you do that? So simple functions form a sub-collection of this collection of sets. Okay, and therefore we use a limiting process. This is done by approximating, by introducing the lower and upper approximations of such functions by simple functions. We have already shown that this is possible, that you can have a lower approximation of a given bounded measurable function over a set of finite measure. We can approximate from below and from above by what are called simple functions. And for simple functions, we can define the lower integral and the upper integral. And then we can use a limiting process. Now, you recall the special case of Riemann integral, where we have been approximating the function by step functions from above and from below. Step functions are what are called simple functions. It's a very special class of simple functions. And then we have looked at the limiting process of the lower approximations and the upper approximations, or what you call the supremum of the lower approximations, supremum of the integrals of the lower approximations, and infimum of the lower integrals of upper approximations. And then when they are the same, we said the function is Riemann integrable. Just we shall recall the whole thing once again, then it will be clear. So if you are working on bounded measurable functions over a set of finite measure, here once again I want to recall that when we defined Riemann integration, we were looked at bounded functions on intervals. Okay, so it fits into this frame. It's essentially a generalization of the whole idea, but now instead of working on what are called step functions, we'll be working on a larger class of functions, namely the simple functions. Now the third step is go beyond this. So we extend now further to, now we are going to drop that, require that it's a bounded measurable function, to general non-negative measurable functions extend further to general non-negative measurable functions over a measurable set. Set defined as the supremum of lower approximations of the measurable function by bounded measurable functions. Which vanish outside a set of finite measure. So here we are not assuming that the measurable set is of finite measure. Extend further to general non-negative measurable functions over a measurable set defined as the supremum of lower approximations of the measurable functions by bounded measurable functions which vanish outside a set of finite measures. In short, what you are doing is you started with 1, then used 1 to get 2, and now use 2 through approximations of functions of the class mentioned in 2. We go to the third class, namely for general non-negative measurable functions. Okay. Then the integral is non-negative. This is coming out of the assumption that the function is non-negative. But maybe infinite. That's a major gain. So you are able to define integral for functions which are not necessarily bounded. Okay, so that's the next stage. Now we have got rid of 2 major constraints from Riemann integral, namely the function is in the Riemann integral, the function is defined only on a bounded interval, and the function itself is a bounded function. And these 2 things we have got out from, and we would have generalized in this way. But the strategy is use the first one, define here, use such functions to approximate to come to this stage, use this class of functions to approximate to the third stage, and then you get the integral. Now all these approximations of integrals, you see, you are approximating by functions, so it is a pointwise approximation that you are talking about. Now the question is whether the limit would exist, and that limit is what we are going to call the integral. Okay, so we will now further make some definitions like what are integrable functions. So we will briefly look into the Riemann integral again to get the feeling how the generalization is. We say that a general measurable function is integrable over E over a measurable set E if integral mod f is finite. Now for such functions, we also prove the following. Lebesgue integrable functions. These functions are called Lebesgue integrable functions. Lebesgue integrable functions form a linear space. Six, we prove that forms a linear space. Lebesgue integral is a monotone you know what a linear functional is? So from this linear space to the set of reals, so it's a functional, it is also a linear functional, and further it is also monotone. That means if the function is monotonically increasing, then the Lebesgue integral of the function is increasing, and vice versa, and also when it is decreasing. 7. So all this involves talking about the limits, because we are making approximations. And it is through approximations of the functions and their integrals we are going to the integral of the general function. So it's actually there is a process of what you call interchange of the limiting process and the integration. Therefore, you naturally ask whether it is valid. So we look at establish conditions under which a sequence of integrable functions integrable functions fn a sequence of integrable functions almost everywhere, converging pointwise almost everywhere. On E, F ensures that the integral also so what you have is this: Fn converges to F pointwise almost everywhere on E. Now you know how to define the integral of Fn because they are integrable functions. Okay. Now, the first question that you ask is this integral convergent? Okay, it converges to a finite number or to infinity. I mean, both can happen. So is that then that can be defined as the integral of this, or in other words, we are so that we have limit which is equal to integral. So, see, if this is assured, then you see it makes sense to talk about this as the integral of F. That is what we. So, that's our plan. Okay. So, essentially, this part deals with it. See, you see that this interchange of integration and the limiting process is not assured in all cases. Therefore, it needs to explore the conditions under which such a change of integral and the limiting process is valid. Okay. So, that's our So you see that in general, the interchange of the integral and the limiting process that is what you call the limit jumps over the integral. Is not valid. So you can give some examples where it fails. Actually it fails, and therefore we cannot make use of that. So what we need is we have to look at. So what we do is, so we have to explore where this interchange valid. That leads to some fascinating theorems, right? So this leads to some fascinating results, namely one, A, the bounded convergence theorem, B, the monotone convergence theorem, C, the Lebesgue dominated convergence theorem, the Lebesgue dominated and the fourth one, D, the Vitali convergence theorem. And all these results are based on the Egreff's theorem. All these are based on now this is roughly the theme of what we are going to do, and it's nice to understand the sequence in which we proceed. And generally when you do mathematics in analysis, this is the general strategy that one adopts. So that is worthwhile to note how these ideas have been pursued and pushed to work for a larger class of functions. So let me just write down the theme. So this is where we start. We start with simple functions. And from there, we go to the next layer, namely what are called bounded measurable functions. Functions over a set of finite measure. So that's the second stage. So simple functions are essentially bounded measurable functions over a set of finite measure. Now it's quite obvious how you approach this. You take a function here, approximate it by simple functions. Okay? And then the integral can be extended provided everything works. So the third layer or further extension on this is for general non-negative measurable. Now you see, these are approximated using simple functions. These are approximated using bounded measurable functions over a set of finite measure. Okay, and therefore you can get the integral of these functions of this kind. So what you have is, if you start with a function of this kind, then you can get this. So the next part is to go for what are called integrable functions. Okay, so that's a larger class. So here we have put this non-negative, which is no restriction at all, because in general you can write f to be equal to f plus minus f minus. Okay, and then if everything works, you see that integral f can be written as integral f plus f minus, provided both these are not infinity. Okay, if both of them take infinite values, then there is ambiguity about this. Okay, and that does not happen if you assume this. Finite. You assume that, then this doesn't. Okay, therefore, for such functions, you can extend this integral of f as integral of f plus minus f minus, because you know that for positive functions or non-negative functions, the integral is 1, and you are assured that this difference is well defined, and therefore that well defined number can be attributed to integral of f. That is possible, and that's the strategy adopt. Now, in all this process, we have what is called the limiting process. Limiting process is, both the integration and limiting process simultaneously working on the sequence of functions. Okay, and then there is the general question of this. We interchange the limiting process and the integration. Will this hold? So what one does is this, that it happens not in general, but under some conditions, and those conditions are explored in these theorems, namely the bounded convergence theorem, the monotone convergence theorem, the Lebesgue dominated convergence theorem, and the Vitalik theorem. So that is what we plan to do next. Okay, right? So we will explore this part as our next strategy. Now let us briefly recall what the Riemann integral is. That's something. This is again, after once again we are recalling it. We have looked at it several times, and possibly in this context we once again look into it, and that would possibly help you to recall where we stand and how we see it. Okay. Okay, I want to make some special remarks. That is the next thing that we do. Okay, so what we have f defined from some closed bounded interval AB whose measure is b minus a. As you know, real valued function on that AB closed and bounded and f a bounded real value. These are the essential assumptions that we make. That is why there's an awful lot of constraints when we defined Riemann integral. Now, the Lebesgue integration actually helps you to get out of that and do it in a more general setting. So, what you have is this: let P be a partition Xn be a partition of the interval A. That is A equal x naught B. So this is the condition that you have on x naught, x1, x2. So you set points on the interval AB in this way, and then you define for this two numbers, namely L to define as and UFU FP this is capital MI and the other one is small mi, where small mi, the infimum of fx over xi minus 1 and capital Mi is defined as the supremum of fx over the same Okay. So obviously you have this. You see that L F P is less than or equal to US. Not only that, one can prove if P1 and P2 are two partitions of AB, then you have L F P1 is less than or equal to U F P2. So all the lower sums are bounded by the upper sums. Okay, so this is something that you have. Okay, now we define the following. So we define what is called the lower and upper integral. Okay, so the lower integral, so we put R here because later on we are going to have the Lebesgue integration also to come, and to tag that what we are talking about is the Riemann integral. So the Riemann lower integral, this is defined as supremum of LPF a partition of supremum taken over all partitions of the interval AB, and the upper integral is again upper Riemann integral. So let me use that word for the time being, at least, because we don't have to use it for far too long. But at the moment, I think better to distinguish between Lebesgue integral and Riemann integral. So let us do that. For details, you should refer to the earlier discussions on Riemann integration, and the upper integral is you have put a bar on top, here you have put a bar below, so that is the lower integral. Infimum of UPF over P, a partition of AB. And you know the supremum and infimum that is mentioned here exists because LPF for over all partitions is bounded by any upper integral. Similarly, Any upper integral is bounded by this, and each one of these is bounded below and above. I mean, there is no problem to establish that, because we are working on what are called bounded functions. Okay, fine. So now we defined f to be Riemann integrable if that's the definition. So this is the definition that we accepted as Riemann integrability, and then we looked at all the properties of that, and you know that these integrals exist, and if they are equal, then you say f is Riemann integrable, otherwise it is not Riemann integrable. Okay, so that's the first thing. Now, one thing that you should observe is this, that the step functions that we have used, because if you recall the definition of the looking at the approximation to f, so in this case you see that f is approximated from below by the following function, namely, what is it? That by L by phi defined by put phi p partitions, where phi p is defined by sigma sigma mi chi of the interval and from above by psi p defined by, where psi p is mi chi or if you want you can use this, right. So these are the upper and lower approximations that we made to the solution, right. One, you can write more clearly this. plus I equal to 1 to 3. Now, you see, these are step functions, or we will now define what step functions are. And these are step functions, and these, through the limits of these step functions, we work on the integral, or through the we define integrals for these step functions, and then get rid of this. Okay. And we said it is conditional provided these upper and lower integrals are equal. Yeah. So that's something what we have done. Now we shall write down more generally what all this is. So we will define what a step function is. Simply says that on the interval xi minus 1 to xi, the function takes a constant value. So it defines some steps. Okay. That is related to the given function. Okay. So let us. So now we define what is a step function. A real valued function phi on AB is said to be a step function if there exists a partition P of AB and numbers C1 Cn and for I less than or equal to n, Ci if xi for I ranging from minus 1 and equal to Cn if xi minus 1 okay. So this is the step, right? Okay, right. And for these functions, L is equal to sigma 1 to n ci minus 1, and which is the same as u. So for step functions, the lower sum and the upper sum are the same. Therefore, these are Riemann integrable. Okay. So the step functions are Riemann integral. Now we can define the Riemann integral of f to be equal to infimum of phi, where phi is a step function and phi is less than or equal to. So the infimum is taken over all step functions on the interval AB such that it is less than or equal to, is bounded above by f. And similarly, the Riemann lower upper integral is defined as supremum of is bounded below by all step functions bounded below by. Okay, so that is the definition that we make. Now remark, I want to make a remark. All step functions are simple functions. But the converse is not. So what you have is this. You have, these are all what you call simple functions. Now you have a subclass of this which are called step functions. See, the reason why the Riemann integration is not able to deliver is because the infimum and supremum that you take are on a smaller class of functions. Okay, and therefore you see that one cannot guarantee that the upper and lower Riemann integrals of f are going to be equal. This is not possible. I mean, there are examples which you can give, and I will just start working on an example, and then our objective is now to go beyond this limitation. It is in this context that we did lot of exercise to overcome this. We introduced a concept of measurable sets, whatnot, Lebesgue measure, so that for intervals, the Lebesgue measure is essentially the length of the interval. So here, in these approximations that we have used to define the Riemann integration, we were working on intervals. There the measure that we were using was only the length of the interval. So we didn't have to go beyond that. Okay. So to get hold of a larger class of functions here and then define the limit using that, we had to do all this exercise. Okay. So you have to appreciate the effort that was taken to overcome some of these problems, and our objective will be to what is of interest would be, having done such a enormous exercise by introducing the Lebesgue measure, etc., does it serve the purpose, or are we to get much better results than that are available for Riemann integrals? Okay, there are two things that we expect. What is that? One, for Riemann integrable function, the Lebesgue integral should coincide with the Riemann integral, so that Lebesgue integration is a genuine extension of the concept of Riemann integration. That is one important thing. The second thing is that our reach should be much more, in the sense that given functions which are not Riemann integrable should be amenable to the new concept of integration. So let us just recall one of the beautiful functions that we had to look at. So take the Dirichlet function. We define this as follows. This is actually the characteristic function of Q intersection. Q is the set of all rational numbers. So you are defining the function that is fx equal to 1, x belonging to, if x is a rational number, and on the interval 0 to 1 and 0 otherwise. That means at all irrational points on the interval 0, 1, f is 0. Now, let's see that the LPF for any partition is equal to 0, and UPF for any partition is equal to, because you see that the function, you take any interval of the type xi minus 1 to xi, you see that it is there is a rational point in that interval. So also there is an irrational point in that. Therefore, the infimum of the function on any interval is 0 and the supremum is equal to 1, and consequently what happens is that okay, this is there exists a rational number and an irrational number in any interval so that says that the infimum is equal to 0 of f is 0, sorry, LPF is 0 and UPF is equal to. So that shows f is not Riemann integral. It's a simple function which is not Riemann integral. But it's a simple function because it takes only two values, namely either 0 or 1. Okay, right? Now we can look at an approximation which gives you some insight into the results that we are talking about there. You know that the set of rationals is countable. So recall that the set of rationals is countable. You see, a lot of these intricacies come from the structure of the real line. That is at the back of everything. It's very important to realize that. That's why one should know very clearly what is happening on the real line. Okay. Therefore, you can enumerate it. Zero one. So k equal to now define Fn. by one for x and equal to 0 okay, otherwise. So Fn takes values 1 at q1, q2, etc. qn, and at all other points it takes the value 0. Okay. Then Fn has finitely many discontinuities. Therefore, Fn is having only a finite number of discontinuities. Also, you have mod Fn less than or equal to 1. Takes only two values, 0 and 1. Therefore, you see that Fn converges to F pointwise. 0. That's quite easy to see. The limit function f is not that means the interchange of the integration and the limiting process is not valid for this function. Okay. So one of the possible remarks that I can make here is that observe that Fn does not converge. This is easy to prove. Uniformly there is no uniform convergence. Okay. That is one observation. That now we will investigate this scenario in detail later. Okay, but it's a very nice example where you have a sequence of functions which are Riemann integrable but does not converge. The integral does not converge because the Riemann integral of, if you stay within Riemann integration, the Riemann integral of f is not different. And you can see how we get over this problem in the case of Lebesgue integration. Okay, so that we will be revisiting this example whenever we need it. So just keep this in your mind always. Okay. Thank you very much. So we'll continue with the definition of the Lebesgue integration next time.